Modern air warfare is defined less by speed and firepower than by information. The aircraft that controls what is seen and when it is seen controls the engagement before the first missile is launched. This reality has reshaped military aviation over the past 4 decades, giving rise to one of the most consequential technological shifts in modern warfare: stealth technology. Stealth does not make aircraft vanish from the sky. It reshapes how aircraft interact with detection systems. Instead of overpowering enemy defenses through brute force, stealth aircraft aim to delay detection, disrupt tracking, and compress an adversary's decision window. The result is not invisibility, but asymmetry. The side that sees first gains control over timing, positioning, and escalation. To understand how this works, it is necessary to examine the physics of radar detection and the engineering compromises that stealth aircraft are built around. Radar operates on a straightforward principle. A transmitter emits electromagnetic waves that travel outward until they strike an object. Part of that energy reflects back toward the source, where it is received, processed, and converted into information about distance, direction, and relative motion. The strength of the return signal determines how easily the object can be detected and tracked. Traditional aircraft designs unintentionally cooperate with radar. Flat metal surfaces, exposed engines, vertical tails, and external weapons all act as efficient reflectors. Early jet fighters prioritized aerodynamic stability, structural simplicity, and weapons capacity, not electromagnetic behavior. As radar technology improved, these aircraft became increasingly visible across longer distances. Stealth technology intervenes at every stage of this interaction. Its goal is not to defeat radar systems directly, but to manipulate how radar energy behaves when it encounters the aircraft. This begins with geometry. The external shape of a stealth aircraft is engineered to redirect radar waves away from their source. Instead of reflecting energy back toward the radar antenna, angled surfaces scatter it laterally or upward. The effect is similar to light striking a slanted mirror rather than a flat one. The energy still exists, but it does not return in a usable form. This requirement drives the distinctive appearance of stealth aircraft. Smooth blended surfaces replace sharp angles. Vertical stabilizers are canted. Panel alignment is tightly controlled. Even minor geometric deviations can produce disproportionate increases in radar signature. Internal weapons and signature discipline. Weapons storage presents a major challenge. External pylons and munitions generate strong radar reflections. Stealth aircraft solve this by carrying weapons internally, deploying them only briefly during engagement. During those moments, radar visibility increases, which is why stealth missions rely heavily on timing and sequencing, engine inlets, and canopy treatments. Air intake design is another critical factor. Jet engines contain rotating compressor blades that act as powerful radar reflectors. Stealth aircraft shield these components using curved intake ducts that prevent radar waves from reaching the engine face directly. This design sacrifices some airflow efficiency but dramatically reduces radar returns. The cockpit canopy also contributes to radar visibility. Modern stealth aircraft use conductive coatings embedded within the canopy material. These coatings reflect radar energy while remaining optically transparent to the pilot, preventing the cockpit cavity from acting as a reflective chamber. Geometry alone cannot eliminate radar interaction. Radar waves still strike the aircraft. The next layer of stealth addresses what happens to that energy after impact. Radar-absorbent materials are applied to the aircraft's surface to convert electromagnetic energy into heat rather than reflection. These materials rely on carefully engineered molecular structures that dissipate radar waves across a range of frequencies. The effectiveness of these coatings depends on thickness, composition, and environmental conditions. These materials must balance electromagnetic performance with structural durability. Coatings that absorb radar energy often degrade under thermal cycling, moisture exposure, and mechanical stress. Maintaining stealth therefore becomes a logistical challenge as much as a design achievement. Operational readiness depends not only on flight hours, but on environmental exposure. Extended deployments in harsh climates can increase maintenance demands, reducing sortie rates if not carefully managed. Stealth, in this sense, extends beyond the aircraft itself into sustainment infrastructure and operational planning. Early generations of radar-absorbent material were fragile and maintenance-intensive. Exposure to weather, heat, and mechanical stress degraded their performance. Modern stealth aircraft use more advanced composites, but the trade-off remains. Stealth aircraft require extensive upkeep to preserve their low observability characteristics. Particular attention is paid to seams and edges. Gaps between panels act as unintended antennas, re-radiating radar energy. Manufacturing tolerances for stealth aircraft are therefore significantly tighter than for conventional designs. Surface alignment is not cosmetic. It is operational. Radar detection is not the only threat stealth aircraft must manage. Infrared sensors track heat rather than electromagnetic reflection. Jet engines generate intense thermal signatures, making heat management essential to survivability. Infrared detection has grown increasingly sophisticated, particularly with the proliferation of imaging infrared sensors capable of distinguishing aircraft against complex backgrounds. These systems do not rely on emissions from the target. They passively observe thermal contrasts, making them difficult to counter through electronic means alone. Stealth aircraft therefore treat thermal management as an integral design constraint. Reducing infrared visibility does not eliminate detection, but it lowers engagement probability, especially at longer ranges. As with radar, the objective is to delay classification and tracking, rather than prevent observation entirely. Stealth aircraft mitigate infrared exposure through exhaust design and thermal masking. Engine exhaust is cooled by mixing with ambient air before it leaves the aircraft. Exhaust nozzles are shaped to distribute heat over a wider area, reducing peak temperature contrasts. Some designs place exhaust above the aircraft body, shielding it from ground-based infrared sensors. Flight profile also influences detectability. High-altitude flight exposes aircraft to long-range radar systems with minimal interference. Stealth aircraft often operate at lower altitudes, using terrain and atmospheric clutter to degrade sensor performance. Mountains, urban environments, and weather introduce noise that complicates radar tracking. Electronic warfare systems allow stealth aircraft to interfere with enemy radar and communication networks. These systems can inject false signals, distort radar returns, or overwhelm processing systems with noise. While jamming does not eliminate detection entirely, it degrades the quality and reliability of targeting data. These systems operate dynamically, adapting to the electromagnetic environment in real time. Rather than broadcasting constant jamming signals, modern platforms employ selective interference, activating only when necessary to avoid revealing their presence. This approach preserves stealth by minimizing emissions while still degrading hostile sensor performance. Electronic warfare also serves a defensive role by protecting Allied aircraft operating in the same airspace. Stealth platforms can act as forward nodes that shape the battle space, suppressing threats before they affect less survivable assets. Crucially, stealth aircraft are designed to operate with minimal emissions. They rely on passive sensors to detect enemy radar activity without revealing their own position. This allows pilots to map threats while remaining electronically silent. The effectiveness of these systems depends on integration. Modern stealth aircraft fuse data from radar warning receivers, infrared sensors, and off-board intelligence sources into a unified operational picture. The aircraft becomes a node in a larger information network rather than a standalone platform. This integration extends beyond the aircraft. Stealth platforms are designed to operate as part of distributed combat networks, sharing sensor data with other aircraft, surface units, and command centers. In many cases, a stealth aircraft may detect and classify a threat without engaging it directly, passing targeting information to another platform better positioned to respond. This division of roles reflects a shift away from platform-centric warfare towards system-centric operations. Stealth aircraft are no longer evaluated solely by their individual performance, but by their contribution to broader information architecture. Two aircraft exemplify the current state of stealth aviation: the F-22 Raptor and the F-35 Lightning II. Both rely on the same physical principles, but their design priorities differ. The F-22 was developed during a period when air superiority against peer adversaries was the primary concern. Its stealth profile is optimized for frontal engagement, allowing it to approach enemy aircraft undetected and strike before being targeted. Speed, altitude, and maneuverability remain central to its design philosophy. The F-35 reflects a different strategic environment. It prioritizes sensor fusion, battlefield coordination, and multi-role flexibility. Its stealth enables deep penetration into contested airspace, where it gathers intelligence, conducts precision strikes, and supports other platforms. While it sacrifices some aerodynamic performance compared to the F-22, it compensates through information dominance. Detection technology continues to evolve. Low-frequency radar systems can sometimes detect stealth aircraft at extended ranges, but they lack the resolution required for precise targeting. These systems may indicate presence without providing actionable guidance. High-frequency radar remains necessary for fire control, where stealth is most effective. Some emerging sensor concepts aim to exploit non-traditional detection methods, including multi-static radar networks, passive radio frequency sensing, and space-based observation. These approaches seek to detect stealth aircraft indirectly by observing disturbances in the electromagnetic environment rather than relying on direct reflection. While promising in theory, such systems face significant technical and operational limitations. Data fusion complexity, environmental noise, and limited targeting precision constrain their effectiveness. Stealth design continues to adapt alongside these developments, reinforcing the iterative nature of the competition between detection and evasion. This dynamic creates an ongoing technological competition. Advances in radar drive refinements in stealth design, improvements in materials, computational modeling, and manufacturing techniques continue to push the threshold of detectability. Stealth technology also carries strategic consequences. It alters deterrence calculations by introducing uncertainty. An adversary cannot reliably know when stealth aircraft are present, how many there are, or what they are targeting. This uncertainty complicates defensive planning and increases the psychological burden on air defense operators. This uncertainty reshapes deterrence dynamics. States equipped with stealth capabilities gain options that are difficult for adversaries to counter preemptively. The inability to reliably detect or track penetrating aircraft forces defensive systems into reactive postures, increasing operational stress and reducing confidence. At the strategic level, stealth complicates escalation control. The presence of undetected aircraft can alter perceptions of vulnerability, influence crisis decision-making, and increase the risk of misinterpretation. These effects extend beyond tactical engagements into broader security calculations. At the same time, stealth is not invulnerable. Detection does not guarantee interception, but it increases risk. Stealth aircraft operate within carefully planned mission profiles that account for sensor coverage, engagement zones, and escape routes. Success depends on coordination, intelligence, and timing. Stealth technology therefore occupies a unique position in modern military capability. It is neither an offensive weapon nor a defensive shield, but a means of shaping perception. By controlling what is observed and when it is understood, stealth alters the tempo of conflict before physical force is applied. The future of stealth is not defined by complete invisibility, it is defined by complexity, making detection unreliable, making tracking expensive, forcing adversaries to deploy layered systems rather than single solutions. In this environment, air combat becomes less about physical confrontation and more about information control. The aircraft that manages signatures, emissions, and data flow gains decisive advantage before weapons are even employed.